Good evening, everyone. My name is Jermaine Marshall, and I am a second-year PhD student attending the University of Notre Dame in the Social Sensing Lab. And my paper is titled MoodSensitive Truth Discovery for Reliable Recommendation Systems. So to begin, just a little brief overview of what social sensing is. So social sensing has emerged as a new paradigm of applications for cyber-physical systems, and this essentially means we have humans in the loop this time. So typically, physical sensors do not consider humans in the most sort. And so a physical sensor can be something as simple as you walking through a Walmart or a Target door and detects you're walking and opens the door. However, we want to focus more so on social sensors, which we report data ourselves through social networks, our mobile devices, or GPSs. And so as a result of that, recommendation systems have also emerged as a way to recommend the best and formal information to users. And so what we're trying to do with our approach is try to tie in social sensing and recommendation systems into a new model. So just a few examples of social sensing applications that are out there. So just using crowds, us as sensors of the environment, we have online social media networks such as Facebook, Instagram, Twitter, Foursquare. We have geotagging applications such as people reporting traffic jams, people reporting potholes in the streets. We have disaster reports such as the Japanese earthquakes that happened recently. And we also have different traffic monitoring. And so those are just a few examples of some of the social sensing applications where we have humans that are actually taking an active part in reporting the information of the physical environment. So I'm going to emphasize a problem that has grown in social sensing. So as humans tend to sometimes report unreliable information. And whether this be intentional or unintentional, we don't know that as far as in social sensing environments, such as social networks. And so we want to solve this problem that's become known as the truth discovery problem in social sensor networks. And by solving this problem, we want to be able to actually be able to recommend the most reliable, the most truthful information to users. And so this is where recommendation systems tie in, because we want to ensure that when something is being recommended, we want it to be factual. We want it to be an unbiased, truthful fact that comes out of that. And so this is where we start to tie this in. And so I'll start with the basic approach to the truth discovery diagram. So we have people. Here we have their devices that we have. We have the GPSs, we have the iPad. So this is the smart devices and the people, and this is who to believe, right? And then we have different arrows pointing here to the claims that make. They have claims on textual data, we have numeric data, we have images that we can post online through social networks. And then we also have, these are all can be seen as truthful information. But then we have sometimes where humans don't report the most reliable information. So this is a photo taken of a shark in the street. It actually circulated on Twitter during a flood, and people actually believed there was actually a shark in the street. But this information was found to be false. But it was actually propagated on Twitter for a good while before this information was seen to be false. And so we want to actually solve this problem, getting rid of or actually seeing that this information is false before it gets too out of hand and reported and retweeted or shared across multiple areas. And so in response to this, we've developed what I like to call a mood-sensitive truth discovery approach, to where we actually consider emotional bias into the equation, because what we noticed is with the original truth discovery solution, there was only consideration of whether a claim was true or false. We had no other features involved, whether it was emotional or timeliness. There were no other features involved, and it was just whether it was true or false, without even considering a lot of the unbiased emotion that's considered in that. And so we came up with a mood-sensitive solution, which actually says whether the user or the claim is excited, sad, angry, and how this affects the truth discovery solution. And so just a little background of related works in truth discovery so far. We had the basic model in IPSN 12, which was we call the regular expectation maximization algorithm that only considers, as I said before, whether a claim is true or false. We've also had a streaming paper in ICDCS 2013, which considers streaming data into the equation. We have conflicting claims. Recently, in SmartComp 2016, there was an emotional aware paper that was published by us. But the thing about the emotional aware paper was it considered 3 dimensions, which was true, false, and emotional, but it didn't consider the types of emotions. So we don't have whether it's positive emotion or negative emotion. We just assumed 3 different variables, true, false, and emotional, and it wasn't a multi-dimensional approach. It just was unidimensional in that sense. And so we come to the RecSys 2016 with the new mood-sensitive paper. And so Again, the best performing baseline in the past is the SmartComp 16 paper, the emotional aware expectation maximization algorithm. What I'm showing you here is a visual representation of the model. And so what we have here is the event that took place. We use different crisis events or different events that may happen in the real world. In this particular case, we use the Brussels bombing for example as an event. And then we form a bipartite graph here that shows the sources making particular claims on a particular event. And when we run this through a maximum likelihood estimation approach, and we want to find out is what the probability that a claim is true, false, or emotional. And so that was the previous solution. So going toward the new solution, we have 3 definitions that I want to point out. So we have positive claims. Positive claims are claims that have a positive sentiment or more so words that express the positive sentiment. Negative claims is the exact opposite of claims that show negative sentiment or words to express that. And then we have neutral claims, which are claims that essentially do not satisfy the requirements of positive and negative claims, or essentially they're neutral. They don't have any emotional bias in them whatsoever. And so we had a bag of words to use a set of both positive and negative mood words obtained from recent literature. And so these bag of words includes a lot of the typical words you find in positive sentiment like happy, excited. Negative sentiment words is angry, sadness. And we built a classifier on that based on a lot of Twitter data that we gathered from 4 different real world events that have taken place in the recent, since 2015. And so the particular MoodSensitive solution that we have here is, what you're seeing is SM, the input is SM, which is called a source mood matrix. It basically says whether the source reports a claim to be, whether the source is mood sensitive, mood neutral, or they just didn't make the claim at all. And then they have the SC matrix, which is called the source claim matrix, that says whether the source actually reported this claim or didn't report that particular claim. And then what we're trying to find out, the output is the hidden variable Z. So we want to know at the end whether this information that we gather is true or false based on the information that we have that's from the sources that's mood sensitive or not. And so I want to describe a little about the likelihood. We derive a likelihood function for the mood sensitive expectation maximization algorithm, which basically says the likelihood function represents the likelihood of the observed data, which is the source mood matrix and the SC matrix, the source claim matrix I just mentioned, X, and the value of the hidden data, which I just observed, which would be the Greek alpha, the Greek symbol up there that looks like a Y, which equals the probability based on the current estimation parameters that we have. And so that's what we're trying to find is the new estimation of the parameters from the model. And so what I'm showing you now is the mood-sensitive EM algorithm. And so we have 2 steps. We have the expectation step and the M step. And the E step begins with a for loop. It just actually computes the likelihood of the current estimation of the model parameters. And then we have the N steps, which takes which maximizes the E step on the new estimates given the current model parameters. And once we put that into those for loops, then we try to decide based on certain thresholds, which in our case we observe in our data that 0.5 is a threshold that works best to see whether a claim is actually true or false in our framework based on the mood of different sources and claims. And so the evaluation, the real-world applications. So these are the data sets that we use. In our particular sets, we use the Paris bombing from November of 2015, the Baltimore riots from April 2015, the Oregon shooting, and the most recent event was the Brussels bombing event. And we use these particular data sets because they actually filter in a lot of information at any given point in time. It results to crisis scenarios, and we found that we could get quite a bit of actual good data that we could test our model on using these different events. And so just a little bit of description of our data. This data was collected from different time intervals depending on the event. And so some of the search keywords we used in our particular data set was the Brussels attacks explosion, Paris attacks ISIS, Oregon shooting Umpqua College, and the number of tweets and number of users we tweeted. And so we actually had a framework that we used to collect a lot of this data. And so the framework that we use is actually called Apollo. So Apollo is a system that we use at the University of Notre Dame to collect a lot of different tweets based on a given geolocation, and based on the keywords that we use in the OR framework. So I could specify any typical location, any number of keywords, and given a particular range, I can get as much data as I want, let the algorithm run for as many days as I want to get the information we need, and it comes into us as a JSON formatted file. And so for the evaluation metric, we use the normal approach to this. The evaluation metric, we have accuracy, precision, recall, and F1 score for our evaluation metrics. And our evaluation results, as you can see, in our evaluation, the MoodSensitive scheme has significant gains in all areas of our approach that outperform the baseline, the regular expectation maximization algorithm, True Finder, sound development approach. The Brussels-Barman showed 19% gains in accuracy, 13% in precision, 16% in recall, and a 19% in F1 measure, which is exactly the results that we wanted to see for this particular experiment. And it was the most recent event that happened this year. And we've ran our results on the other experiments. Due to time constraints, I didn't post all of them, but similar results are observed in the Paris attacks, Oregon shooting, and Baltimore riots events that occurred as well. And so for our future work and discussion, we want to kind of focus on the fact that sources may be dependent upon each other in some social system applications, and we want to consider the particular dependencies of this in future work and assessments. We also did not assume dependency between claims, but we also know that claims may be inherently correlated. So if an event happens in a particular area, people in that general vicinity may be more likely to have the most truthful information, as opposed to if I'm in Boston, the event happens in Boston, and then I report on it way in LA, then more than likely I'm getting information from another source, and we don't know if that's reliable or not. So we want to focus on that. We also plan to use this model, estimate its usefulness and recommending reliable information to users on particular things such as products. So we want to actually run our data, our model on different data sets and actually try to see if we can recommend the most useful information that we find reliable in particular recommendation systems in this case. And in conclusion, truth discovery, as I said, is a big challenge, and social sensing and emotional information is very important, especially when we're trying to recommend the most reliable, the most suitable information for users that are using these particular social sensing platforms, such as social media, geotagging applications. When a disaster happens, we want to be able to recommend the most reliable information. And the proposed mood-sensitive scheme explicitly incorporates the mood neutrality of claims and the mood sensitivity of sources into this rigorous analytical framework, because we want the claims that are the most mood neutral, the most unbiased claims, and we don't want sources that are particularly sensitive to the events that happen, because when they are, they can a lot of times report biased opinions which can be false and can be charged with emotion. And we evaluate the schemes again through 4 real-world case studies and social sensitive applications to verify the results of our experiments. And if you want to learn more on social sensing, my advisor has a book, Social Sensing, Building Reliable Systems on Unreliable Data, that's available for purchase. And we also want to have acknowledgments for the National Science Foundation Graduate Research Fellowship Program. Yeah, thanks. So, thank you.
Thank you very much. Questions?
Thank you for the talk. Given the number of recommender systems that are not about a ground truth, but about opinion, you know, there isn't a truth as to whether a movie is better or worse or a product is better or worse. There's still a notion of deception and an attempt, you know, biased reviews, just as we've heard in the first talk, just reviews and ratings that are designed to influence rather than to reflect a person's true intent and true belief. Could these techniques be extended or applied somehow to find things that are not objectively true, but that are relatively true, to detect cases where people are being dishonest in things that are subjective?
Yeah, so that's actually what we want to focus on. We want to see if our approach based on the mood-sensitive model, because what we're seeing is that people are more likely to have, even if they may report truthful information, it may be emotionally biased, emotionally charged, A lot of times, even when they report false information, that's emotionally biased too. And so what we want to do is hopefully expand this model to kind of handle cases where we can actively see the types of emotion that was may influence that, so we can actually see in the cases of maybe where you're saying like movie reviews or what may be inherently intentional bias towards a certain, let's say, a particular movie that's trying to maybe decrease the ratings on it or decrease reviews, maybe one person, and that information is perpetuating down. So we want to actually be able to see when that is occurring. So that's one thing we hope to do in the future work as well.
Other questions? The middle.
Hi. One of the motivating cases was about detecting this in images too, right? And right now it sounds like the technique mostly is looking at sort of word features to infer mood and emotion and possible opinion. So I'm assuming you're thinking about how to detect these signals of potential emotion or deception in pictures too. And I was wondering if you could talk a little bit about how you were thinking of going after that. And also like if these data sets are available, if there's like a ground truth data set of claims that have true and false attached to them, because that'd actually be pretty useful to a bunch of communities.
Yeah. So in my particular model, we actually developed a particular ground truth file for all of our particular data sets that we had. So we actually went through and actually saw which data was actually true, false, which was actually shown to be, which we saw to be mood sensitive and mood neutral. And so we went through that. And so we used a particular ground truth for that to kind of measure against our particular model and measure against the current baselines for that. And so let's say what the goal is, to the point that we don't have to use the particular ground. We don't make our models good enough to the point that where we don't have to use the particular ground truth from that, and we actually get factual information from that. So what these results showed was that we can get actual pretty accurate information. We can see what information is actually true or false or not, but we also want to improve our results upon that. So we want to, right now it was at about the 80th percentile on 80% on precision, 80% on accuracy. So we want to actually improve that to get a 90% measure on that, because right now the current baselines don't perform as well, but we want to improve our model to where it performs even more significantly better in that approach.
More questions? Okay, then thanks to the speaker again.